And today's lecture, we are going to learn about things called eigenvectors and eigenvalues. And they are going to be super important when it comes to understanding properties of materials, solving systems of linear equations, analyzing circuits, studying Markov models if you're a gambler. They're just eigenvalues and eigenvectors. They are the first PageRank system that Google introduced. They're behind a huge amount of stuff. So I'm going to start with an example of something interesting or something that I find interesting. And it's going to lead up to eigenvalues and eigenvectors. So here's a matrix A. 2, 3/2, -1, -1/2. Now, if I compute A, what A does to the first standard basis vector, then I'm going to get 2, 1, 2 minus 1. Now, if I then say, well, what happens if I apply A again? So what is A of 1, 0? Then that's A times 2 minus 1. And that is 5/2 minus 3/2. And if I apply A 3 times to the vector 1, 0, that is A times what happens if I apply A twice to the vector 1, 0. So that is A times 5/2 minus 3/2, which is 2.75 minus 1.75. So if I apply A once to the standard basis vector 1, 0, I get this. If I apply it twice, I get this. If I apply it 3 times, I get that. If I apply A 4 times to the standard basis vector, I get 2.85 minus 1.875. If I apply A 10 times to the standard basis vector, I get 2.9980 approximately, minus 1.9980. If I apply A 40 times to the standard basis vector, I get 3 minus 1.82 times 10 to the minus 12, and minus 2 plus 1.82 times 10 to the minus 12. Similarly, if I were to apply A 40 times to the vector -1, 4, I get 9 minus approximately good, 9 minus 9.09 times 10 to the minus 12, minus 6 plus 9.09 times 10 to the minus 12. And in general, if I apply A 40 times to the vector x1, x2, I get something which is very close to 3x1 minus 2x2 times the vector 1, 1. So actually, let me back off on that. So what we see is you have this matrix, and if you apply it over and over and over and over and over and over to a vector, that is converging to a specific vector. If I apply this matrix over and over and over again to that vector, I converge to a specific vector. So the natural question is, how can you see what's going on? Or is this just an exercise in MATLAB? And so here's the observation. So the matrix 2, 3/2, -1, -1/2 is equal to 1, 1, 2, 3 inverse times the matrix 1, 0, 0, 1/2, 1, 1, 2, 3. So the first question is, how did I get that decomposition? So given this matrix, how could I figure out that it's written in this form? In practice, what I did in my own office was I built A by doing this. But this is going to have to do with diagonalizing matrices. We're going to be doing that soon, but not now. But if I have this, A squared is something -1, 1, 0, 0, 1/2, the matrix. That's A. And then the other A is going to be inverse 1, 0, 0, 1/2 A. So I have this matrix here, and then I have its inverse here. So what does this times its inverse equal? The identity. So I have that A squared is 1, 1, 2, 3 inverse times 1, 0, 0. Was it really -1/2? It was +1/2. 1/2. 1, 0, 0, 1/2 times 1, 1, 2, 3. So that's 1, 1, 2, 3 inverse. I can multiply these. 1 times 0, 1 times 1 plus 0, 0 plus 0, 0 plus 0, 0 plus 1 over 2 squared, 1, 1, 2, 3. Now, A cubed is going to be A times A squared. So A is that inverse matrix times the diagonal matrix times the original matrix. So that's the A. A squared, that was the inverse matrix, 1, 0, 0, 1 over 2 squared times the original matrix, A squared. What is this matrix times that matrix? The identity. So I get that A cubed is 1, 1, 2, 3 inverse, 1, 0, 0, 1/2, 1, 0, 0, 1/2 squared, 1, 1, 2, 3. So that is 1, 1, 2, 3 inverse, 1, 0, 0, 1/2 cubed times 1, 1, 2, 3. So in general, do you feel that you can compute the 40th power of A? Yeah. So the 40th power of A is going to be 1, 1, 2, 3 inverse, 1, 0, 0, 1/2 to what power? 40. 1, 1, 2, 3. So this we can multiply out. So here we have 3 minus 1 minus 2, 1. 1, 0, 0, 1/2 to the 40th. 1, 1, 2, 3. Yep. A to the 40th is 3 minus 1 minus 2, 1. 1, 0. 1, 0. 0, 1/2 to the 39th. 0, 3 times 1/2 to the 40th. So 3 minus 1/2 to the 39th. 3 plus 3 times 1/2 to the 40th. Minus 2 plus 1/2 to the 39th. Minus 2 plus 3 times 1/2 to the 40th. And in general, a to the nth power, what would a to the nth power be? So this would be n minus 1. So you can do this in general. But we see that a to the 40th times 1, 0 is, well, we've got, that's the first column, 3 minus 2. And if you put this into your calculator, you're going to get those numbers. And it removes the mystery of why they were equal. Looking at this, you're like, is it a coincidence that these are equal? And for this one, I had minus 1 and 4. So if I were to multiply this by minus 1, 4, I would get minus 3 plus 12 would be 9, plus small plus small. And here I would have 2 minus 8 is minus 6 plus small plus small. So that would be a times a to the 40th times that, which is what we had. And in general, you see what a is going to do to any vector as the iteration count goes up. This is the kind of stuff that's behind all those cool fractal drawings that you see. What they're doing is they have a map of the plane, and they apply it over and over and over and over again, and they keep track of where points go. That's when they make those fractal pictures. They are just applying a map from the plane to the plane over and over again to different points. Are there questions on this example? The take-home on this is pretty cool. And we would like to know how to find that. And beyond that, real-world examples rather than just something like this pulled out of thin air. Questions? Yes?
The first line on that blackboard, the matrix with 3, -1, -2, 1. Where did you get those values from?
So that was this inverse. So I claim that the inverse of 1, 1, 2, 3 is 3 minus 1 minus 2, 1. So there are two ways. One thing would just be to check that 3 minus 1 minus 2, 1 times 1, 1, 2, 3 equals the identity. Because this was the general form that a to any power was going to be, that a to the n was going to be the inverse 1, 0, 0, 1/2 to the n, that matrix. So this was the inverse of this matrix. So you can check it works. Otherwise, you would have to actually do the algorithm. And at the end of the day, you would get this. Or you would have to memorize. So there is a formula for 2 by 2 matrices, which you can just memorize. It has to do with computing the determinant, dividing by the determinant, flipping some terms around. If you have a good memory, just memorize the formula for a 2 by 2 determinant. Write down, for a 2 by 2 inverse, write down what you think your memory is telling you, and then double check it. So if I were in your shoes, for a 2 by 2 matrix, I would have memorized the thing that led to this. I would then check it works, because I don't actually trust my memory. Are there other questions? OK. So what's with this decomposition? So this leads to a bigger question of eigenvalues and eigenvectors. So we start with a definition. So consider a linear mapping. A nonzero vector x is an eigenvector of L if L of x equals lambda x for some lambda. And we'll deal with real eigenvalues for the moment. Lambda is an eigenvalue of L if there is a nonzero vector x so that the linear mapping on x is lambda x. And we say lambda x is an eigenvalue, eigenvector pair of the linear mapping. So an eigenvector is something so that when the linear mapping acts on it, it doesn't change direction. It just gets longer, or it gets shorter, or it changes direction, possibly getting longer or shorter. So let's do some examples first. So example, L goes from R2 to R2. L of x is reflect x about the line y equals 2x. So this is a nice linear mapping. If I ask for its standard matrix, so if I commit to the standard basis for R2, 1, 0, 0, 1, and I ask to represent this linear mapping in terms of that basis, I get that the standard matrix is minus 3 halves, minus 3 fifths, 4 fifths, 4 fifths, 3 fifths. Okay, so I would like to compute L of 1, 2 and L of minus 2, 1. So that means I want minus 3 fifths, 4 fifths, 4 fifths, 3 fifths, times 1, 2. And I would like minus 3/5, 4/5, 4/5, 3/5, minus 2, 1. Okay, so what's the first product? What's the first entry on the right-hand side? 1. What's the second entry? Okay, the second product. Hold on. Minus 3/5. Yep. What's the first entry on the right-hand side for the next one? 2. And the second entry? Minus 1. Okay. So we just figured out. That t of 1, 2 is equal to 1, 2. And t, or L, so we figured out that 1, 2 gets sent by L to 1, 2, and minus 2, 1 gets sent by L to 2, minus 1. So that means that L of 1, 2 is equal to 1 times 1, 2, and L of minus 2, 1 is equal to something times minus 2, 1. What is it? Minus 1. So this tells us that 1, 2 is an eigenvector with eigenvalue equal to so go up there, 1. And minus 2, 1 is an eigenvector with eigenvalue negative 1. Geometrically, we have this line, y equals 2x. If I take the vector 1, 2 and project it onto the line, what do I get? The same thing. If I take the vector 2, 4 and project it on the line, what do I get? The same, 2, 4. If I take the vector minus 1, minus 2 and project it onto the line, it's the same. If I take the projector minus 3, minus 6, minus 3, minus 6. So let's just check that's true. So L of t times 1, 2. This is some scalar multiple of 1, 2. It should stay unchanged geometrically, right? Because it's a linear mapping, this is some silly number. What can I do? Take it out. So t, what is L of 1, 2? 1, 2, because I've done that calculation. So I've just figured out that L of t times 1, 2 is t times 1, 2. So t times 1, 2 is an eigenvector with eigenvalue 1 for any non-zero t. And I'll get back to that in a moment. Okay, that was understanding the first eigenvector. Here is the eigenvector minus 2, 1. I'm reflecting about this line. Where does minus 2, 1 get sent? The opposite. And what about minus 4, 2? The opposite. And minus 6, 3? The opposite. So geometrically, it makes sense that you're just taking this vector and multiplying it by minus 1. So that's the explanation for this is why minus 2, 1 is an eigenvector with eigenvalue minus 1. And similarly, t times minus 2, 1 is also as long as t is non-zero. So if I said that minus 2, 1 is an eigenvector, could you give me infinitely many other eigenvectors? Yeah, just multiply them by infinitely many non-zero numbers. So it's actually going to be a subspace of R2. The eigenvectors with eigenvalue 1 are part of a subspace. Okay, now there's one question. What's all of this stuff about non-zero t? Here's a matrix. For $20, quick, give me a solution. I'm not really going to give you $20. For $20, quick, give me a solution. I haven't given you A, and pi is arbitrary. Quick, what's the solution? The zero vector. What about ax is square root of 2x? Quick, give me a solution. Zero vector. So quick, give me a solution. Is this feeling kind of like an empty exercise? Did it have anything to do with A? No. With that example, it may have been confusing, but it shouldn't have felt empty. We got two geometrically meaningful directions. We understood what the eigenvalues meant geometrically. All of that stuff should not have felt completely empty and meaningless. This is like, come on, you knew I didn't mean a zero vector. The zero vector is too easy. If you allowed the zero vector to be an eigenvector, then any number is an eigenvalue. There's nothing special about 1 and minus 1 for that matrix. So we do not allow the zero vector to be an eigenvector. OK, so another example. L goes from R2 to R2. L is project x onto the line y equals 2x. And this has the matrix 1/2, 1/5, 2/5, 2/5, 4/5. So here's the line. Given a vector, we drop down and we get that. So I seek two eigenvectors, v1, v2. Geometrically, please give me what you would hope would be two eigenvectors and what you would hope would be the corresponding eigenvalues, and then we will check it afterwards. So without looking at the matrix, just looking at the picture, you're looking for can you find vectors which, when you act on them with that action, you get a number times the vector? Yes?
The thing parallel to the line and one perpendicular.
OK, so parallel and perpendicular. So here I'm collinear. You would expect that L of v1 should equal what? v1. And so you would hope that the eigenvalue would be, and in which case the eigenvalue is 1. L of v2, if it's perpendicular, what does v2 get sent to? 0 vector, which I can write as something times v2. What is that something? 0. I did not say anything against 0 eigenvalues. I have no problems with 0 eigenvalues. They're important. I do have a problem with 0 vectors being called the eigenvector, being called an eigenvector. So geometrically, that's what we expect. Now we can check 1/2, 2/5, 2/5, 4/5, 1, 2. To see if this, I claim it's an eigenvector. To check if it's an eigenvector, I have to actually do the multiplication. 1/5, thank you. So 1/5 plus 4/5 is 5/5 is 1. 2/5 plus 8/5 is 10/5 is 2. One-fifth, 2/5, 2/5, 4/5 minus 2, 1 is 0. Now, if I try a rotation, so I take a vector and I rotate it by theta. So rotate counterclockwise by theta. Can you think of any vector which, after rotation, is just some number times the original vector? So here it's important that I'm not rotating by 360 degrees. If I rotate by 360 degrees, I have the identity matrix. And that certainly has you can come up with vectors that get sent to a scalar multiple of themselves if it's the identity matrix. If it's not rotation by 360 degrees, can you think of any vector which, after rotation, is just some scalar multiple of its pre-rotation? No. So this has no real-valued eigenvalues. It does have complex-valued ones, but it has no real-valued eigenvalues. OK, so how would we go about finding eigenvalues? So before I get into finding eigenvalues, I just want to ask you a quick question. Here's a matrix 3, 1, 1, 1, 3, 1, 1, 1, 3. Show that 1, 1, 1 and minus 1, 1, 0 are eigenvectors. And find their corresponding eigenvalues. How do you show this is an eigenvector? You have to do that multiplication. And you have to do that multiplication. So please do that multiplication while I erase the blackboards. Okay. What is A times 1, 1, 1? 5, 5, 5. So that is 5 times 1, 1, 1. This has lambda equals 5 as its eigenvalue. A times minus 1, 1, 0 is what? Beautiful. So that's 2 times minus 1, 1, 0. This has eigenvalue is 2. So if someone gives you a matrix and a vector and claims it's an eigenvector, you can quickly check. Now, let's go back. So how could we find these magical creatures? How do we find eigenvalues and eigenvectors? So let's start with the one I began with. 2, 3 halves, minus 1, minus 1 half. I seek x so that ax equals lambda x. The problem, I don't know x. What else do I not know? I don't know lambda. But I can start. So 2, 3 halves, minus 1, minus 1 half, times x1, x2 equals lambda times x1, x2. Multiplying out the left-hand side, 2x1 plus 3 halves x2 equals lambda x1 minus 1 half x1, minus 1 x1 minus 1 half x2 equals lambda times x2. I have two equations. How many unknowns? 3 unknowns. Okay, the fast solution is x1 equals x2 is 0, in which case lambda can be anything. But are these even linear equations? My unknowns are x1, x2. What's my third unknown? Lambda. Now, if you feel like it, what you can do is you can solve the first equation for x1, determining it in terms of x2 and lambda. You can plug that in. Now you can solve the second equation for x2, and you're just going to get something that lambda has to satisfy. equation 1, get x1 in terms of lambda and x2. Plug in to equation 2, get that there's a non-zero, actually, get that x2 equals 0, or lambda equals 1, or lambda equals 1/2. But this is a pain for 2 equations. It would be really nasty for 3 equations, and so on and so forth. So this can be done, but I don't recommend it. So what we're going to do is we're going to do the classic thing of rewriting the problem until we have something that we can actually handle. And ideally, what we'd like to do is we would like to separate the problem of finding lambda from the problem of finding the eigenvector. Because it would be really nice if we could just, instead of trying to find the eigenvalue and the eigenvector simultaneously, if we could somehow just find the eigenvalue and then find the eigenvector. Okay, so I seek non-zero x and a lambda so that ax equals lambda x. That's what I want. That's the same thing as I seek a non-zero x and a lambda so that ax minus lambda x is what? 0. That's the same thing as I seek non-zero x and a lambda so that a minus lambda times the identity times x is the 0 vector. The intermediate step was to write this as minus lambda times the identity times x, because if you ever write on an exam a minus lambda x equals 0, you will get spanked. You may not subtract a number from a matrix. Don't do it. OK, I seek a non-zero x and a lambda. So here, I'm talking about, so question, when does bx equals 0 have non-zero solutions? B is square. If B is invertible, are there non-zero solutions? Okay, so if B is invertible, are there non-zero solutions of bx equals 0? So B being invertible means that B is equivalent to what? When you do the reduced row echelon form? The identity. So 1, 0, 0, 0, 1, da, 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 da. So when you try to solve bx equals 0, you're going to carry that augmented matrix to reduced row echelon form, and what's going to be on the left-hand side? So the solutions are there, how many solutions are there? One. All right, so if B is invertible, are there non-zero solutions of Bx equals 0? No. I am seeking a non-zero solution of a homogeneous problem. I am seeking a non-zero solution of a homogeneous problem. If there's going to be a solution, to be such a solution, A minus lambda I must be, can it be invertible? No. Must be non-invertible. That's if and only if the determinant of A minus lambda I is what? 0. So my matrix was 2, 3/2, minus 1, minus 1/2. The determinant of 2 minus lambda, 3/2, minus 1, minus 1/2 minus lambda is 2 minus lambda times minus 1/2 minus lambda plus 3/2. I want this to equal 0. What kind of equation is that in lambda? Quadratic. How many solutions is it going to have? 2. And you can check that, solve it out, and you're going to get that lambda has to be 1 or 1/2.